Okay, anyway, let's get to the slides and let me just check it's changing. Okay. Yeah, so today we will go over the system properties. Yeah, last time we go over the property of convolution. So it turns out that convolution is just like a multiplication. So this notation actually makes sense because it's like a multiplication and it satisfies the three laws that we like on scalar multiplication. So it's commutative. So x convoluted with h, same as h convoluted with x. And it is distributive. So this x convoluted with h1 plus h2 equal to x convoluted with h1 plus x convoluted with h2. And it's also associative. So this x convoluted with h1 convoluted with h2 parentheses is same as you have x convoluted with h1 first, then convoluted h2. Okay, so it's really like multiplication. You can just write down a string of things convoluting with each other, and it's well defined. And even the ordering doesn't matter because it's commutative. Okay, so that's the property of convolution, and it's very nice. And we'll start to describe the LTI systems in terms of their impulse response. So we'll write those block diagram, and inside the block, we just write the impulse response because we know the impulse response totally describe the LTI system. And then we can like combine swapping the box in this way. So h1, h2, then you know they are same as h1 convoluted with h2, then you can swap them around, etc. Okay. So that's about the properties of convolution. It will be very useful. And then we talk more things about those impulse responses. So as we said, the impulse response totally characterizes the LTI system. So the four properties we talked about in chapter 1 can also be described in terms of H very nicely for LTI system. Okay. And so we start one by one. The first one is this memory property, and wait, it doesn't work. Okay, yeah. So the memory property, and it actually have a definition for memoryless. So a system is memoryless if the output at any time only depends on the input at the same time. Okay. So in terms of H, it turns out that it means so you want the output on some time depends only on the input of the same time. Then that only happen if and only if, so for discrete time, if only if this impulse response h of n equal to 0 when n is not equal to 0. And so maybe I draw a picture to get some intuition on this. So obviously you can check the equation. So for example, we check y of 0, and you just write down the convolution equation. And that's summation k from minus infinity to infinity, h of minus k and x of k, because n equal to 0 now. And you want this thing to only depend on x of 0. Then obviously all those h of minus k need to be, all of those h of k need to be 0 other than when k equals to 0. Okay. And it can also be seen in a picture way by just doing the convolution thing we've been doing, right? So we can plot, so it just plot this equation in a convolution way. So I think it's even more intuitive. So we plot this in terms of k, and we have x of k is whatever x of k, like this. Right, this is some function. Then we will also plot in terms of k. Then we will have h of minus k. Okay. So this will also be something. And we want this of h of minus k only pick out the x of k at k equal to 0, then it must be imposed at k equals 0. And we're actually plotting discrete time, so it should be like a finite amount here and 0 other place. So when you do the convolution, remember when you do convolution, you want to, okay, let's go back to this. Sorry, this, yeah. So you want to line up the k, okay, so I should actually, okay, so maybe let's do this. Let's do this again. Let's line up the k. Yeah. So we have, okay, so k here, and okay, so this is h of minus k and x of k, and x of k is whatever thing, whatever input. So you want your h of k to don't pick up the x of k when k not equal to 0. So your h of k needs to be like one single spike at k equal to 0 here. Okay, and then you multiply together and so on. Then your y of 0 will only depend on x of 0. Okay, and you can see that's the same thing when you consider different y, different n. Okay, so when you have different n, then this h of 0 will get, so when n increase, then this spike will shift to like some place at k equal to n, and you will pick up the x of k at k equal to n, etc. Okay, and yeah, so that's the intuition. And so if your h of n is 0 when n is not equal to 0, then as we said, it only has value when n equals to 0, then it's proportional to this delta of n. Okay, and yeah, so we can just write h of n equal to k times delta of n. And so this is the condition for your discrete time LTI system being memoryless. You just need to check is your h of n proportional to delta of n for some constant k. And also you can plug in this back to your convolution, and you will find out that in that case your y of n will just be proportional to x of n. Okay, so this should be big K, or this should be small k. But anyway, now let me write down the note. So yeah, so this should be small k, and this should be small k. Yeah. Okay. And the continuous time is similar, although it's a little confusing because it should go to infinity. But continuous time, you change the delta of n to delta of t, and similar logic work out. Okay. So let's not go to the detail, but this delta t will go to infinity, and you need to actually do integration, but to make the meaningful things out of it. But anyway, so similar logic will let you go to this conclusion, and when you do the convolution with this delta of t, you find out that your y of t is proportional to x of t. Okay. So memoryless system is very simple. It's just described by this constant k. Okay. Question? Not. Then let's go to the next one. So invertibility. Okay. So how do we describe the invertibility of the LTI system? So first we need to get the extra property that we will not prove. Is I think you are actually doing this in homework. Okay. So there is an extra property being that if the LTI system is invertible, then that inverse is also an LTI system. Okay. So this is not immediately obvious, but you will do this in homework. So as we are skipping ahead a little bit, so first you need to remember the invertibility of any system means that there exists another system that when you string them together, you back to doing nothing or doing identity, right? So remember the meaning of invertible means that, so you do your system, then Then there is another system, so your x, y, and there is another system that has w also equal to x. Okay, so yeah. So yeah, so there if you are invertible, then there is this inverse system. Okay, so yeah. So this part. So let's say this is s and there is s minus 1. Okay. Yeah. But it didn't say the inverse, so it didn't say the system is LTI, then the inverse system must also be LTI. But that's actually true. So, and you can prove that in the homework. And anyway, so assuming this is true, then we can see that if the LTI system is invertible, then it's invertible if only if there exists another LTI system described by H1, such that H convoluted with H1 equal to delta function. Okay. Because delta function, we didn't quite say, but it's easy to check, and we'll see this in more detail much later, that this unit impulse function is actually the unit impulse for the identity channel. That's because, and what I mean is that if you convolute your input x of n, whatever input x of n with the delta function, then we'll get back to your x of n. And same for the continuous time case. Okay. And anyway, so I guess lots of things we need to prove here. So first, why is this true? Because now we use the properties about convolution we used before. So now we consider you have your input x of n, then you go through your first system h of n, then go through a second system with h1 of n, and because of the associative property, that's same as your x goes through a system with h convoluted with h1, and so this is delta of n, and we can that, and you can also check with calculation easily that x convoluted with the delta equal to x, okay, for whatever x. So yeah, so we prove the if direction, right? So we prove that if h1 convoluted, h convoluted with h1 equal to delta, then they are the inverse of each other, basically. Also because of the commutative. So h1 will be an inverse of h, and also because it is commutative, so h will also be an inverse of h1. And okay. And the other way around, so the only if direction, then we need to use this line up here. Okay. So for I think yeah. So if so the only if direction means that we're trying to go from invertible to this thing. Okay. So but let's see. So it's invertible, then it has inverse, and we also say the inverse is LTI. Okay. And we can say this LTI inverse, then we call this the inverse is LTI, then is described by some impulse, and impulse h1. Then we can check with basically the same thing that h convoluted with h1 must be equal to delta. Okay. Okay. Any question? Otherwise, then continuous time, then that's basically the same thing. You just change n to t. Okay. So because it's also the same convolution thing, and in continuous time, you also have the x convoluted with delta of t, x of t convoluted with delta of t equal to x of t for x of t. So I should write that down. So for continuous time, we also have, where is my pointer here? x of t convoluted with delta of t equal to x of t. This is a relation we will see throughout the whole course. Okay. Hey, any question? If not, then let's see an example. Okay. Okay. It's a bit confusing because we have more delta function, but anyway, I guess it's also a proof of what we claim. Okay. So if we have h of t equal to delta of t minus t naught for some constant t naught, and then you have y of t to even do the convolution, and we'll do some shifting thing, and we'll see that equal to x of t minus t naught. And so then we say this is invertible because we can find the inverse h1. Okay, so we can look at this a bit about the property. So you see that this delta of t minus t naught basically will do a time shift on x, right? So yeah, so your input x and the output will just be a time shift of x because you go from x of t to x of t minus t naught. And since this t minus t naught will do a time shift of minus t naught, then if you do t plus t naught, it will time shift this back to the same original x. And that's indeed what will happen. So if you have y convoluted with h1, then we'll time shift this back to y of t plus t naught that will equal to x of t. And you can also check that if you convolute those two delta functions together, then you get back to the delta function of no time shift. Okay. And another example. Now we go to discrete time, and now we have h that is less trivial. H of n equal to this unit step function u of n. Remember, this is 1 when n is greater or equal to 0, and 0 okay. And this h of n will actually give you an accumulator because when you do x convoluted with h, then you have the summation of n u of n minus m, and because n minus m needs to be bigger than 0, so the summation will cut off at n. So we are just summing x of m. So previously we do k here, but we write the m here for whatever reason. But anyway, so we are summing x from minus infinity to the current time n. So this is the accumulator, you are summing all the x up to the current time. Okay. And this thing also has an inverse. So you can also look at this a little intuitively. So accumulator, you are summing everything. So the inverse of a summation is taking a difference. So you will have this difference operator. So you have delta of n, which will keep your input. Then you minus delta of n minus 1. So basically you minus your input at the previous time step. And okay, yeah. And so what happens? So we can see this actually happen here. So y of n convoluted with h1 of n. Then you do the distributive property. So you have y of n convoluted with delta that give you y of n back. Then you have y of n convoluted with delta n minus 1. That's y of n minus 1. Then you take a difference. And you see that if you have this summation thing, and then you take a difference of 2 steps, then you get back the current step. Okay. Because yeah, so you go back to x of n. So you see that this h1 of n actually give an inverse system of this x of n, h of n, and you also check the relation is correct. So you convolute those two things together, then you back to the delta of n. I believe this is one of the properties when we talk about discrete time. Is it? Okay, maybe not. But but anyway, you can check this is also true. Okay. Any question? Not. Then let's go to next property. Okay. We have no question. We are very on track. Next property, causality. Okay, so causality is basically saying us the memory thing, right? And anyway, so first as a reminder, wait, we didn't say. I guess I need to say. So remember, a system is causal if the output at some time n doesn't depend on input at the future time step. Okay, and so anyway, let's draw this. Let's draw this y of 0 again. Okay, because it's time invariant, so the drawing time y equals 0 is the same. So we draw this convolution plot of k, and we have whatever x of k. And then we think about what your, so we have x of k here, right? K, and we have h of minus k here. And we want our y of 0 only depend on x of k for k be greater or equal to 0. So your h of k should have 0 for all the negative part and like positive on those parts, right? But this is of h of minus k. So h of k should, when you undo this time inverse, then your h of k, wait, did I get it correct? No, sorry. Okay, I got it in reverse. So, excuse me, yeah. So h of minus k, so our y should only depend on the previous x. So it actually has, also erase this. Okay, yeah, sorry. So I got this the other way around. So our y should only depend on negative x. Okay, so we should also only depend on previous x. So your h of minus k should only have value for k less than 0, and it should be 0 all here. And when you invert back, then your h of k should also only have positive here. Okay, and you can think this other way around as h of k is the impulse response, of a system. So you are thinking you hit your system with x. So now you think about x of n and h of n. Right. Let's see. I need to find some way to draw. Control P. Okay. And yeah. So the other way to think about this is you hit the system with your delta function. You hit with x equal to delta of n. Okay, so now this is n. And then you have some impulse response. Then your system is causal. So the response should, because there was nothing happen before n equal to 0. And so your system is causal, so your system should have no response until you actually hit it with something, right? So your h of n should only have something after this n equals to 0. Okay. So anyway, so the both way point out to that if your system is causal, then your h of k should be 0 for all. H of n should be 0 for all those n less than 0, or in terms of k, but you are just changing n to k here. So we also see the h of k is 0 when k is less than 0, but k and n are dummy variables, so it doesn't matter. Okay. And bottom line is this is the relation you want to look for testing causality. And you can also plug in this back to your convolution, and you'll see that you get some relationship on how your y of n should look like. So your y of n is convolution is a summation of k of xk h of n minus k. but now your h of n is cut off for this n less than 0, so your upper bound become n, or you can do the commutative and swap h and k, and you see the k cut off at 0. Okay, and also similarly you have this continuous time case. Actually, my drawing is more like continuous time case, but anyway. Any question about the explanation of the causality of system? So system is causal if only if h of n is 0 for n less than 0. Okay. Or h of t is 0 for, oh, so I have a typo here, so it should be t here. So t. It should be t here. Okay. Question? If not, I think causal is, we don't have too much to say. Okay, then the next one is, wait, Okay, yeah. Then the next one is more tricky, is stability. So I think it's also tricky in the previous chapter and tricky now. And first we recall the definition of stability we have is that is the BIBO condition. So if a bounded input, then the output is bounded. Okay, so this means stable. Stable if only if we always have this BIBO property. Stability is stable if only if whenever our input is bounded, output will also be bounded. And bounded means that here exists a number b that those are all less than b, etc. Okay. And here, now this is a little hard to see, but we'll prove it next page. Such that, so the system is stable once again if only if h of n can be written in some condition. And this condition is absolutely summable. Means that if we sum the absolute value of h of k, okay, and now k from, so all the value k from minus infinity to infinity. So if this summation is a bounded value, then our system is stable. As we can also look at a bit about intuition. So, but the intuition is if you, so remember h is the impulse response. So I guess the intuition is that if you hit your system with impulse and the response is kind of finite, and then your system is stable. Okay. And similarly for continuous time, the system is stable if only if your h of t is absolutely integrable. Means that you take its absolute value and you integrate through all the time, and that give you a finite value. And okay, so there is something very tricky here that you need to be careful. So I guess it's more tricky in the continuous time case. So first, this is the absolute value, not the absolute value square, and yeah, so that's different. Yeah, sometimes absolute value square is converge, but absolute value doesn't converge, and so basically they are inconvertible. If you refresh your calculus a little bit, and so that's one thing. Remember, you are only taking absolute value. And another thing, as we will see an example very soon, is that you want the integral to converge, and that's different from their value being so integral converge is different from like h of tau being finite at every value, because you can have h of tau has a very narrow peak, and you integrate over it, and it's actually still finite. Or you can also have h of tau being finite everywhere, but when you integration, because your integration interval is infinite, so h of tau being finite, and you integrate through everything, then it becomes infinite. Okay, so remember, you want the integration to be finite, not like their value being finite. Okay, and I think it's actually confusing because there has a bounded input, bounded output. So you want to integrate on h, but you don't integrate on x and y on this input and output condition, right? So remember this x and y bounded here is okay. This is the we want this exists b such that x of n is less than b for all n, right? And yeah, so this bounded condition is different from this absolutely integral condition. It's just incomparable. So we don't want h of t to be bounded. We want it to be absolute value integrable. So this integral and this summation is important. And yeah, so don't confuse this bounded and integral absolute value integrable. They are different conditions. Okay. Question so far. Okay. And anyway, if there is no question, then let's do say a small proof here. I guess we only have half proof here. But anyway, so for the discrete time, let's see why this absolutely summable condition H means the system is stable. And okay, so the reminder, we want stable means it's bounded input bounding output condition. Okay, and so proof. So we say this condition is if only if. So it has two parts. And so first part, we want to say this condition is sufficient. So if you have this condition, then your system is stable. Okay. Okay. And yeah, so then we try to fill this bounded input, bounded output thing. So we say our system is bounded. So let's say your x of n is less than b for some b and for n. Then let's see what's the absolute value of y of n and y of n. And we start with the convolution thing. So this is just plugging in the formula. There's an h of k, summation k, h of k, x of n minus k. Here we already do the commutative thing. So we swap the h and k around. Remember before we always had x of k, h of n minus k. But now we know h and x are commutative, so we have h of k here, and x of n minus k, that's the same convolution. Then we break this absolute value. We turn it inside the summation. That will actually only make things bigger. Okay? This is by triangle inequality, and we can make it inside the absolute value inside the summation, and then the absolute value of product equal to product of absolute value. So we can put the absolute value on h and the absolute value on x of k minus k. And now we use our assumption here. Okay, so we have absolute value of x of n less than b for n. So this absolute value of x of minus k will less than b for every n minus k. So I'll just write this in with b instead. And what we're left with is the summation k absolute value absolute value of h of k. And we know this is a finite value and b is a finite value, so we end up with a finite value. Okay. So this is the proof for sufficient case, and once again for necessary case is one of the problem. I think it's actually not in homework, but you are always welcome to do some extra problem to see the proof. And yeah, it's not too hard. It's basically that. Anyway, so you want to prove that way around. So you want to say if this is infinite, then there is some input such that output will also be infinite. So you basically try to have the input correct all the absolute value sign here, give you all the absolute value sign here. So when you do the convolution, some y will actually be this infinite value. That's a very fast explanation. Anyway, question about this proof here. And obviously this is only proof for discrete time case, but you can easily get this to continuous time case by just write integral instead of summation. Okay. And then if there's no question here, then let's see this example. Okay. And so let's see two examples of stable and two example of unstable system. Okay. And first we have example of a stable system. And okay. And this is so the example of stable system are those time shift system in either continuous time or discrete time, and we kind of see that. So the system with h equal to delta of n minus n naught or delta of t minus t naught. Okay, so we claimed before. So let's see. Let's try to wait. If I do this, it works. Okay. Okay. Yeah, remember those things. So we say if h equals to delta t minus t naught, then y will just be a time shift of x. Okay. And we didn't do discrete time here, but that will be a similar thing. Okay. And jump back. Okay. And anyway, so yeah. So your h equal to delta minus n naught, then your xy is only a time shift. Then obviously that's stable, because if x is bounded, then y will be bounded by the same bound, because y is only a time shift of x. And they want to check our absolutely summable condition is correct. So we sum over the absolute value of this delta n minus n0 thing. Then it's all positive, so absolute value sign doesn't do anything, and the delta only have a spike of height 1 at n0, so the summation is just 1. Okay, so you see that this is stable, and indeed the h is absolutely summable. Okay, and continuous time is similar. So we say that if you want to have a system being a pure time shift, then its impulse response is this delta of tau minus tau naught. H of t will be delta of t minus t naught. That will time shift your system by t naught, and obviously that's stable. And now we check the absolutely integrable condition, and this absolute sign once again doesn't do anything. Then we integrate through a delta function that gives you a value of 1. That's kind of the definition of delta function. Okay, and so those are stable. And now we see things that are not stable. Those accumulator function. So we have seen in chapter 1 that the accumulator is unstable, because if your input is a constant, then your output is a linear function with time, and that's unbounded. Your output will keep growing. Okay? And the accumulator has h of n equal to u of n, also as we've seen from the previous example here, right? Okay. So here we kind of prove that if h of n equal to u of n, then our system is actually an accumulator. You will accumulate all the x of m up until m equal to n. And let me jump back. Okay. Yeah, so this is the accumulator, and it is unstable. And we can also check its impulse response. So its impulse response will also be this u of n, because you have yeah, because you have inputs as input, then you have delta of n convoluted with h of n. That will also just be u of n. Okay, and anyway, so impulse response will be u of n. Wait, what am I saying? Never mind. Sorry, confusing myself. So yeah, so impulse response is u of n, and then we check whether it's absolutely summable, but it's not, right? Because u of n has non-zero value for all the n from 0 to infinity, and there are infinitely many ones you are summing over, so that's infinite. Okay? And there is a continuous time counterpart of this accumulator, that's an integrator. And so it's y of t equal to this integration of x of tau up to t. And so similarly, you will have your h of t equal to u of t here. And you also see it's not absolutely integrable. Because you do this integration, then you are integrating 1 from 0 to infinity, that's infinity. So this is not stable as predicted. Okay? And let's have a few summary. So we have our, well, those are not time shift, but very similar. So, so if our impulse response are those deltas, then your system is stable because you sum over n or integrating over t. This give you 1. And if your impulse response is u of n or u of t, then it is not stable because you integrate through them or sum over them, then it goes to infinity. And this is an example that we said before. So you look at this delta of t, and you realize that delta of t is actually not a bounded function, because delta of 0 is basically undefined. Delta of 0 is infinite. So this is an example where your impulse response has somewhere infinite, but when you integrate over it, it's finite value. Okay, and u of t is another counterexample. Okay, so the u of t is bounded, so u of t, the absolute value is less than 1. Okay, it should be less or equal to 1. Okay. So this is less equal to 1 everywhere, but when you integrate through it, it's infinite. Okay. So yeah, so you should not look at whether your h of t is bounded. You need to integrate over it or sum over it. That's the condition you want to look for. Okay. Okay. So I think those are the 4 properties in terms of h. Any question? I guess we can go through a quick review. So there are 4 of them. So first is memoryless if only if we are proportional to a delta function. Okay. And the second is invertible if you can find an invertible LTI system. So you want your h and convoluted with your h inverse, it becomes a delta function. The delta function is actually the impulse response for identity system. Okay. And then causality is a weaker condition than memoryless. So you want your h of n to be 0 for every n less than 0 or t less than 0. Okay. And finally, stability. You want your h of n to be absolute value summable. So you sum the absolute value and it's finite, or absolutely integrable. So integration over the absolute value is finite. Okay. So those are the 4 properties. And okay. And obviously you are going to see homework and test on this. Okay. And finally, let's go through something not quite as important. Okay. Oh, so this first. I think we can do this in 5 minutes. Okay. So then we also have a unit state response. So I guess this is more about just a name you need to remember. Okay. So unit state response is very closely related to our unit impulse response. So it's a response of the system when your input is unit step. Okay. So that's the definition. And there are two things you need to memorize. One thing is the unit state response, and another thing is we will denote it as S of n or S of t. Okay. And the point y is not too important because it's a bit too closely related to our h of k. So it's basically you can compute your S of n from h of n very easily, okay? Or h of n from S of n. So here we have this formula. So S of n, we just do the basically a definition. So it's a response when your input is u of n. So u of n as the input, then the output, because it's a LTI system, should be u of n convoluted with your h of n. Okay, so and then you split all this convolution, you find out that this is your h summing from s infinity to k to n. Okay, just because your u of n cut off this at n. And you can, now you see this is like a accumulator, then you find out you can reverse this. So you can also calculate your h from S of n as this difference. Okay. And similarly, for continuous time, your S of t will be integration of h of tau, and h of t will be the differential of your S of t. Okay. And here is some reminder. So your input is a delta function and response is called h, and the input is unit step function and the response is called s. So it's basically mostly about just remembering the names here. And we have 2 minutes to talk about something else. So also just a small concept here. So we have a concept of support. So this is a bit physically motivated. So we think our system is something, we think our input and output mostly will happen in some finite interval. Maybe you are making a phone call and it will start at like 3 o'clock and at 4 o'clock or something. Okay, so we kind of want to describe this kind of phenomena. So say you have like x of t like this, right? And you will start at time step t1, and you will have whatever signal here, and will end at some step t2. Okay, so we just want to describe this phenomena of your x of t happening in some interval. Okay, and so if your x of t look like this, then we say this t1 to t2 interval is your support. Okay, so this interval is support. Okay, and we also have a length of support. Obviously, is t2 minus t1. Okay, and so a little more non-trivial thing is, so you can have a support of your x of t, and you can kind of look at your h of t as a signal too. But anyway, so you can also write your h of t and so h of t, okay, and maybe it's a square response, okay, something. But anyway, so your h of t you can define similarly. You also have a support, and when we do the convolution, then you can do the calculation carefully, and you will find out that the support actually add up to each other. So if x of t has support on t1, t2, h of t support t3, t4, then support of your y being a convolution of x of h will be t1 plus t1 plus t3 and t2 plus t4, and the length obviously adding together. Okay. And similarly for discrete time. Okay. Okay. And sorry for going over a little over time. So I guess any question? Otherwise, we'll have a 10-minute break. Okay, so let's have a break.
我请问一下，之前交的资本作业会发回来吗？
会发回来吗？应该会。他说都没有发回来吗？应该是会发回来。我就问一下助教。应该都是有，是不是？
是这个问题什么问题？就是他说，他这里是说，这个 condition 是 sufficient
and necessary
to 证明它是
BIBO
嘛？对，就是
但我们这里只证 sufficient 嘛。对，就是说如果这个对的话，那你的提升就会 BIBO。
如果不对的话，
就不会是 BIBO。
就不会吗？还是说我们不能总结任何东西？
没有啊，就不会啊。如果不会的话，就不会。那个是那个 necessary 嘛，就是说，对吧？necessary 就是说，如果是 BIBO 的话，就一定是它。那反过来说，如果不是它的话，就不是 BIBO。就是 sufficient and necessary， 所以这样是 equivalent。但不对的部分我们没有证，就是说你可以去看那个问题去证。
就是它是if and only if 的那个关系。
对对对。sufficient and necessary 就是 if and only if 换一个方式说这样。对。
OK。
对。
我在想，如果因为我一开始以为它只是那个什么 if then 而已。
没有了，它是什么？因为我前页的是说因为我之前对今天才改版的，是的，你现在重新下载的话，应该会有写比较清楚。对，就是我把它翻回去。对，这是1分钟的衣服这样子。对。
OK。1分钟1。好的。
因为每个礼拜都在改版。
好。我看一下，还有一个要问。它的那个 support 的那个，其实是什么意思？我还是没有听得很懂 support 的部分。
support 就是看图比较简单吧，就是说我觉得我的这个方向是在一定的区间内有值，那这个区间叫 support。就是说超过这个区间的话，就是小于这个 T1 就全部都是0，然后大于这个 T2 全部都是0。然后这个开始不是0的这个区间，我就叫它 support。
就是你在抓一个区间出来，对啊，就是哪一个方向的 support。
对啊。
所以就是说，刚那个就在说，就是说，假设你从第一个，
就是
从 xt 抓这一个区间出来，
就假设 x 值在这个区间不是0，然后 h 值在这个区间不是0，那 x 乘以 h 就只会在这个区间不是0。
可以理解，好，谢谢。
也不是，看不录。 这次的作业可能今天应该交不完，因为交到differential equation附近。OK， 我等下抓一下。对，看我下一题1章的，1章有一个叫initial rate，好像对啊，还是有应该课本的会议也是吧，对，找一下。然后有书，我不知道跟你的题号一不一样，就是了。我是看新的那一本，但我觉得应该前后吧，反正就找一下，我看一下。找不太到。不是第1章，还是？对，第1章可是因为是 initial race 嘛，有这个东西，就 initial race causal。对。又出一大堆 test property， 是不是？可能一样，又是考几个小题吧。反正也是一样的。对啊，小题也蛮的。哦，那可能要看一下题目，再看一下。等一下我再来看哦。OK， 好。OK。I think it's about time to start. Okay, we'll start here. Yeah. So we're talking about the properties of LTI system in terms of impulse response H. And finally, we'll talk about what happened to the support of your function when you do a convolution. And I think it's quite intuitive to see that the support of your input and the support of your impulse response will add together when you do the convolution. And so the length of your output signal will be adding together of your input and impulse response. And so this is continuous time, and similarly we'll have discrete time will have the same thing, except you have this weird +1 from basic elementary school counting, because it's discrete time and eventually count the number of your things. Okay, so if I draw, okay, so it's a similar concept, except it's discrete. So let's say your signal like this, okay, and x of n and n, and it's from some n1 to n2, and they want to see how many items are actually from n1 to n2 is actually n12 minus n1 plus 1. And so similarly, when you do convolution, then your y will be supported one is n1 plus n3 and n2 plus n4, and you can calculate the length of y will be length of x plus length of h, and minus 1. Okay, so that's support. So any question on the property of LTI system? Otherwise, we'll switch to a very different topic of differential and the difference equations. Okay. And I guess the bottom line here is first we can see the differential equation and difference equations are systems, and hopefully we'll prove today that if you have this condition of initial rest, then your differential difference equation is actually causal and the LTI system. I didn't say causal here, but anyway, let's see what's the differential equation. So differential equation look like this. So I think in this course we keep talking about constant coefficient differential equation. linear constant coefficient differential equation. So linear means that all the x and y here have order 1. Has power 1. So they are linear in x and y. And the constant coefficient means all the coefficients before those x and y are constant. So you have 2 here, 1 here, and then you don't have like some t squared, t here, etc. But anyway, so this is a differential equation. We have dy dt plus 2y of t equal to x of t. And we can look at this as a system. So remember, system is something that you input some function x of t, then you output some function y of t. So you can see this kind of have the flavor here. So if you pick some x of t here, then you can solve for some y of t. Okay, and but it's quite different from what we do before, because before this we usually have a quite explicit formula for y of t. So we usually have like y of t equal to something something from x of t. But differential equations give you like a more implicit specification. So you see that if you give an x of t here, then you need to do more extra work to solve for y of t. So that's something. But so that's good and bad. I guess the good part is differential equation can describe a lot of physical systems. Then the bad part, maybe I should not say bad, but the harder part is that we need to work harder to get our y of t. And actually, you will see very soon that this is not quite complete picture. So to solve the differential equation, just writing down this equation is not enough, because if you just have this relationship between x and y, then there are multiple y that will satisfy for the same x. So, but the system you want, like if you have one input, you want a specific one output. So to make a differential equation into a system, then you need to give more conditions. So you can have a boundary condition or initial condition, but in this course we usually give it initial conditions. Okay. So you need to specify basically the initial values of y at some point, and to make this actually a 1-to-1 relation between x and y. Not 1-to-1. Actually a unique solution for every x. Okay, so let's work through this example and see kind of how differential equation works. Okay. And so we want to solve this for a particular input. So let's say our input look like this: x of t equal to some constant k times is the exponential part, e to the 3t times u of t. So this is an unbounded function, but whatever, this is a function that we can put in. Okay, so this is a crazy exponential part, and you go to infinity with the exponential growth. Okay, and now there are something about differential equation we just stated as true. Okay, and so I think this only works for linear equation, but we only look at linear equations in this course. So first, y of t, we can always write it as a summation of two parts. So a particular equation yp plus a homogeneous equation yh. And yh is a homogeneous solution, means that you are solving for input actually equal to 0. Okay. So it's solving for the, first assume this x of t equals 0, and we solve for a y that satisfies this. Okay, and then we also have the particular solution. That's whatever solution solve this. Okay. Okay, and let's see what the homogeneous solution and the particular solution can be. I believe let's first solve for particular solution. Okay, and and so particular solution, so we want to solve this equation for this input x. And now we see x has this exponential 3t part. And a way to solve differential equation, especially when you have this exponential part, is just guessing your answer has the same exponential part. Okay? So this is, I don't know, kind of a heuristic way to solve this. But anyway, so we guess our solution as this form. So our particular solution has yp of t equal to some constant y times the same exponential e to the 3t. And we just plug in this into our differential equation and see how it works out. Okay, so y e to the 3t and dy dt, so you get a h plus 3 here. Then you have 2y, so 2y. And then you have x of t equal to this thing, okay? K e to the 3t. And now we see this work out quite nicely because everything has this e to the 3t. Okay? And everything has this e to the 3t. And e to the 3t is non-zero, so we can just cancel it. And now we just left with the relation for a whole bunch of constants. So 3y plus 2y equal to k. And that just means y equal to k over 5. Okay? So we find out that for t equal bigger than 0, we can find a particular solution of y of t equal to k over 5 e to the 3t. Okay? That was nice. We guess the solution and the guess is correct. And for the homogeneous solution, then we see that this exponential function works out very nice. So we guess it with another exponential function. So we have the y h of t equal to a e to the st for unknown s and a. And okay, and I should have small s here. Okay, let's mark this down. Small s. Okay, and yeah, so we. So this is a very common thing you do in solving differential equation. You guess the answer and hope the guess is correct, and solve for the unknown coefficient in your guess. And anyway, so our guess is correct once again. So you plug in this back to our differential equation, then you get the HRS from this differential, and have a 2a here. Then you find out this is a e to the st times s plus 2. This should be equal to 0, and so e to the st will not be 0, and so either have a equal to 0 but it's nothing, so it's very boring, or s equal to minus 2. Okay? And we take the less boring one, so have s equal to minus 2, so this is 0, and in that case a can be anything. Okay, and yeah, so your homogeneous solution is a times 2 times e to the minus 2t, and then your total solution, and you need to plus is k or 5 e to the 3t. Okay, so this is your solution, and for t bigger than 0. Okay, and okay, the comment here is this a equal to any. This is a common thing for the homogeneous solution of your linear differential equation, because think about this equation, and you have y times some constant, so you have y go to ay, then then the left hand side will multiply by a, and that will still be 0, right? So if you have so homogeneous solution should always have like an undetermined constant, because if you have y go to ay, then you just have a times this equation, and that will equal to a times 0 equal to 0. Okay, so that's some digression. And anyway, so So our solution for this differential equation look like this. And you see that you still have an undetermined A here. Okay. And that's why we need to set the initial condition. Okay. So if we want to solve for A, then we need to set for whatever initial boundary condition. And the initial condition here we use is initial rest. And that means that your y equal to 0 until your x is not 0. Okay. And our x look at this. So maybe let's also plot this. So x is this crazy exponential function that because of u of t. So this is 0 until your t is 0, okay, and t equals 0 is equal to k, and it will exponential grow to infinity, okay. This is x of t. But anyway, as we say, because of this u of t, so x of t is 0 until this t equals 0. So we assume our y of t is also 0 until t equals to 0. Okay, that's the initial rest condition we are taking. And if that's all, then we have y equal to 0 is 0. And then we plug in this, then we can solve for a. So with this and we have 0 equals 0, and those exponential are all 1, so we just have a plus k over 5 equals 0. Why do we have this extra? I should also erase this. Anyway, and for t bigger than 0, then your y of t will just be k over 5, then your exponent k over 5, and e to the 3t, and then minus your e to the minus 2t. Okay. And for t less than 0, then because we assume this is initial rest, so y is 0 for all t less than 0. So you want to combine this thing with the fact that y of t equals 0 for all t less than 0. Then you put the extra u of t here. Okay. So for all t, y of t equal to this thing. Okay. So any question? This is an example of solving our differential equation with the assumption that it being initial rest. Okay. Actually, okay. And I guess here in this chapter we don't talk about how to solve differential equation too much, because in a later part we will give a better way to solve them with Fourier transform and such. But here we are giving an idea of what is the differential equation, and it has those particular solution, homogeneous solution, and you need the initial condition like this initial rest, and having initial rest, then you can solve for the full condition for solution. Okay. And let's talk more about this initial rest. So it's a little different from, not sure, I think if you in calculus class probably don't use this condition. But anyway, the initial rest is defined as your y of t is 0 until x of t is non-zero. Okay. And so it's very important. So it's different from the usual initial condition, because usually you have like, I guess if you do this in calculus, you will usually do like y of t equals 0 at t equals 0, or y of t equals 0 at like minus infinity or something. But it's different here that this until part. Okay. So our y of t is starting at a very funny time. So because we are seeing it as a season. So your y of t is equal to 0 will be set at this, will depend on your input. It will be set at whatever point your x of t start being non-zero. Okay. And this is what we are saying here. Our y of t at 0 is not set at any fixed point of time. It's y of t start changing until your x of t starting change. Okay, and we'll prove very soon that we have this initial rest condition. Then our differential equation is LTI and COSO. Okay. So any question about the definition of initial rest? Where do I? Let's see. Where do I? Oh. Okay. Okay. Yeah. Question? Okay. If not, then yeah. So we kind of do this in reverse order. We start with the example, okay, and we fill in the definition one by one. So this is the definition of initial rest, and we give a definition of what's the differential equation, or or more generally, we give you a definition of a linear constant coefficient differential equation. Okay. So we will be dealing with those kinds of differential equation in this course. We'll look up them many times. Okay. And so there are a lot of specification here. So nth order means that this dy dt is has at most nth order in this dy dt. So you have dk dt and this k go up to n at most. Okay. So nth order and linear. Linear means that the y and the x are all linear here. So only have y of t and x of t here. So you don't have like y square of t or x square of t here, etc. And the constant coefficient means that all those ak and the bk are constant. So those don't depend on t or x or y. So those are constants. Okay, and the differential equation, and so those are these things. So on the left hand side you have a whole bunch of differentials of y. So you have a dy, so you have dk y dt to the k. So this is a case order differential of y, and the sum and the linear sum together with coefficients ak. And on the right hand side you have also differential of x. So differential of x are to whatever mth order. Okay? So this m we don't care too much because x is input and you can calculate the differential. Okay? So you have dkx dt, and this also sum together with the coefficient pk. So this equation is a general form of our nth order linear constant coefficient differential equation. And those differential equation we'll consider in the course. Okay. And I guess we can look back. So our favorite 2.95. You see this is an example of first order linear constant coefficient linear differential equation. So on the right hand side you have x of t. So you don't have differential here. So m equal to 0. And so right hand side you have n equal to 0 and b0 equal to 1. And on the left hand side you have n equal to 1 because highest order is dy dt, so like one order of differential. And then you have a0 equal to 2 and a1 equal to 1. Okay. So this is a particular example of our this 2.109 very complicated looking nth order linear constant coefficient differential equation. Okay. So those are the equations we hope to solve for. And we give a little more special case. So you can see if we have a special case of n equals 0, then on the left hand side you don't have any differential of y. So you just have a0 y of t here. Then you can move a0 to the other side. then you see that you actually give an explicit formula for y of t. So you just need to do all kind of derivative on x, and you can calculate y of t here. Okay, so that will be easy to solve. And also, if the right hand side is 0, then you are go back to the homogeneous formula. Okay. So homogeneous differential equation means that you are solving this summation of dky, dtk, and they all sum to 0. Okay. That will be homogeneous because whatever y of t is a solution, then that satisfies the homogeneity, right? Then a y of t will also be a solution. Okay. Okay. That's the thing we talk about. I guess we can write it down again. So if homogeneous means that, how do I? Okay. Homogeneous means that y of t is a solution. Then a y of t, and you put it into this formula, then we'll have a summation something will also equal to 0. So a y of t will also be a solution. It's a solution. Okay, so the system is homogeneous. Okay, it's not quite a system because there is no input, but you see that y of t is a solution, then y of t is a solution. So kind of like the homogeneous system we talk about. Okay. And anyway, then there is another name. So the solution to this equation is called the natural response. Okay. 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 With no quadrant, then let's talk about putting things together. So what happens when we have this differential equation and we have our initial race condition? Okay. So that's nice. Actually, so we have our differential equation here, summation ak dky dtk and equal to summation bk dkx dtk, and have our initial rates. So y of t equal to 0 until x of t is non-zero. Okay. So we have this picture here. So we think t is like this and s on t. So your input maybe like the upper line here. So your input stays 0 until some t0. Then your output will also stay 0 until the t0. Okay, and okay, so that's a condition, but actually the way we use it is from this we can derive that this means we can say a lot about y of t at this t0. Okay, and the actual condition we use is that so we assume y of t has continuity and enough smoothness at this t0. So y of t0 is going to be 0 because it stays 0 all the way until here. And I think this can be proved rigorously, but anyway, if you have like nth order differential equation here, then this transition point will be smooth enough such that dy dt and all the way to dn-1 dtn-1 at this t0 will all be 0. Okay. So this actually can, if you want rigorous proof, then you need to do this more carefully, but here we just say the result. But anyway, the intuition here is that all those derivatives, so all the derivatives up to nth order, they are basically continuous at the t0. So you see that for y of t for t less than t0, then all the derivatives are 0, right? Because y is just 0 when t less than t0. So here we are basically assuming that those derivatives are all continuous at the t0 point. So the 0 point will be smooth enough such that at this point is all those derivatives are well defined. Derivatives are well defined, and so it t0 minus value equals this t0 plus value, and is all 0. Okay, so that's what happens when we have initial rates. So all those, so y of t0 and dy dt up to n minus 1 order, those derivatives are 0 at this point. So it's quite smooth here. And something we didn't say is that why do we have this y up down to your dn minus 1 dt n minus 1 is that if you have nth order differential equation here, so let's change to pen once again. So you see you have n here, right? So this is kind of like solving equation with many unknowns. But so nth order differential equation, then you want to solve nth order differential equation, then you need bigger initial conditions or boundary conditions. Okay, so this is kind of like solving an unknown variable. You need, kind of like when you solve an unknown variable, you need an equation in algebra, and we generally you have this kind of thing. So you solve an nth order differential equation, then you need n kind of whatever auxiliary conditions, either initial condition or boundary condition. So that's why you need n value here. Okay, so it's 1 to, so from 0 to n minus 1. Okay, and anyway, so this is what will happen. You want to solve this equation, and you assume initial rates, then you translate your initial rates to that all those differentials at t0 equals 0. And we'll have proof that in that case, then the system, so remember we are describing a relationship between x and y, so this system between x and y, it will be causal in the LTI. Okay, and we'll prove here. So the proof is actually pretty simple, but the notation is a little annoying, so I guess we can skip the details. But anyway, so we want to check this LTI. So LTI and the causal. So we basically just check the conditions. So we want this to be LTI. So first we check it's linear. So we assume some x of t. So we have some x1 of t giving output of y1 of t, and x2 of t giving output y2 of t. So basically x1 of t here will give y1 of t as the solution, and x1 of t, x2 of t here will give you y2 of t as a solution here. Then we check the linearity. So we have some HR, I guess I can call x3, but anyway. So if x of t is a linear combination of x1 of t and x of t, so alpha times x1 of t plus beta times x of 2 of t. Then we just plug in this into this formula, and we see it's very linear, and and that will just equal to the linear combination of the same term with y1 and y2. So you see that alpha y1 and beta y2 is the solution to your alpha x1 plus beta x2. And so those are just you put things in and out of the summation, and the summation linear, so everything's linear. And also differentiation is linear, so everything works out. And you check that the system defined this way is linear. Okay. We also need to check other thing. So we check that will satisfy this differential equation, but we also need to check the initial race condition works when we have alpha x1 plus beta x2. And I think we have time, right? So let's plug a little bit. So now this is a little bit tricky because yeah, let's see. I do this. So now this is a bit tricky because the initial point of x1 and the initial base, maybe draw here. So we have our t here. Okay. So we have initial point of x1 maybe it's on t1, and the initial point of x2 maybe it's on t2. And we saw also generality as assume t2 less than t1, t2 bigger than t1. And so your y1 will also start here, and so this is x1, this is y1, and x2, and your y2 will start here. And yeah, so you see that y1, so your alpha y1 plus alpha b plus beta y2 will also have the initial race against your x1 plus x2, because x1 plus x2 now have the initial race point at this smaller t1, and you see your y1 and y2 also start at this t1, so that works out. Okay, so you also so this alpha y1 plus beta y2 also satisfy the initial race condition for your alpha x1 plus beta x2, and so you see your system is linear. Okay? So that's nice. And then excuse me. And then you can, so LTI, so you check the linear, then you also want to check the time invariant. And time invariant is pretty direct. So you have, you assume some x of t give you some output y of t. Then you just take the differential equation and do change of variables. So you go to t minus some t1, and you see that, well, just by looking at the equation, you see that x of t minus t1 will have the solution of y of t minus t1, because dt minus t1 equal to dt. So yeah. So yeah, so you see that this is time invariant because you do a time shift on your x, then the time shift of y will satisfy your differential equation. And also you check that the initial race will obviously obey your time shift. So because you time shift your x, then your initial race point will shoot by some t naught, and obviously your y will also shoot by the same t naught. Okay, so that works out. And so it's linear and time invariant. And finally, we need to check causal. And check causal, and then we use the thing that we talked about. Excuse me. Then we use the thing we talked about last class. So we check the impulse response of the system. And okay. So we want to check impulse response. So x of t equal to delta of t. And how to solve it, we don't know how to do yet, but we can all just see that the impulse response to this h of t, it must be 0 whenever t less than 0, just by the initial race condition, because this delta of t has delta of t has its initial time point. What? Oh, it's old. Okay. Because delta of t has impulse at t equal to 0, right? So delta of t is t, and this is delta of t. And so delta of t is 0 until t equals to 0. So by initial race condition, the response to delta of t must be 0 until t equals 0. So for all those t less than 0, your y of t, which is equal to h of t, equals 0. And because of the causal condition we set up before, then the system is causal. Okay? And yeah. So we have done our proof. So if our nth order linear constant coefficient equation, which is this, quite complicated summation equal to summation, and also with initial race condition, which translate to the value and up to n-1 order derivative are all equal to 0 at this initial point, then your system is causal in LTI. Okay, that's something to remember. And okay, we're actually a little faster. I guess any questions so far? And the bottom line is we have this equation, and and we have initial race condition. Then the system is causal in LTI. If there's no question, then we should have time to finish the discrete time case. So the discrete time case is not too different. Okay, so we can have a discrete time counterpart, and now it's not called differential equation; it's called a difference equation. Okay. And yeah, so very similar. We have nth order linear constant coefficient difference equation, and but it's discrete, so we cannot take derivative. So we just take basically a time shift here. So instead of dy dt, now we have y of n minus k. Okay? Instead of case order dy dt, now we have y of n minus k and x of n minus k here. So this is a difference equation. So let's say everything again. So sum k from 0 to n, ak y of n minus k. So it's either k will have some time shift on your y. And on the right hand side, we have k sum from 0 to m, bk times x of n minus k. Okay, so that's a difference equation. You can feel that it's very similar to a differential equation, except that you don't have differential, you have difference here. Okay. And similar to the continuous case, you can also write a solution as a particular solution and a homogeneous solution. And the homogeneous solution is a solution to when you put the x part to 0. Okay, so we solve for this. And once again, this will be homogeneous. So if y is a solution, then a times y is also a solution. Okay, for whatever a. And okay, and similarly, we consider the difference equation with the initial race condition, and we will get the same conclusion that is causal in LTI, and we won't run the proof again because it's quite boring. But anyway, we didn't say the difference equation, initial race condition for discrete time, but I think basically the same. So initial race means that x of n, if x of n is 0 until some n0, then it's same. So y of n is 0 until this n0. Okay. So there are a lot of typo issues you should fix. Okay. So it should be breaking here, y of n. Okay. And it's discrete, so this n minus n0, n less than n0 actually have like a finite shift. So we have like at the sum n0, x starts being non-zero, so maybe x like this, and x is 0 all the way here. Okay. And then your y will also be. So if this is x of n and this is y of n, okay, then y of n should also stay 0 until this n0. So So y of n is maybe a lot, depends on the system. Okay. Anyway, so that's the initial rest, and but now there's a difference in here. You see the blue part. So the difference thing is there is no derivative you can take here, and but we still need n conditions. We still need to get n conditions to solve our difference equation, nth order difference equation, and the conditions are here. So all the y, so the ny, so the n different y, that's before your n0 here, should all be 0. Okay. But remember you start with -1 because remember y of n0 is not 0 because x start at n0 and y also start with n0. But anyway, so the previous ny's are all 0. So y of n0 -1, -2 up to -n, those are 0. That's what happens when you have initial rest. And we skip proof here, but if we have those things, the system will also be causal in LTI. Okay. And something I guess good about discrete time system is that it's a bit easier to solve because you can always write your y of n in this recursive relationship. Okay. So this is basically something you can do later on a very easy computer program. So you can you can move things around and just write your y of n as this thing. So this 1 over a naught because y over n has a coefficient with a naught, and this is summation of a whole bunch of x over n minus k. So this you can just calculate. And those only depend on y of n on previous time step. Okay? You have those summation k from 1 to n, y of n minus k with coefficients. Okay? So for every n, you can just calculate your y of n with this thing. So you can just look up all the previous x, sum them together, and then look up all the previous y, sum them together. Then you get this y of n. Then you get next step. Then you do this summation. Okay, so you can do the recursive thing to keep calculating your y of n, and it's recursive, so we call it a recursive equation. Okay, and yeah, so you go one step and one step, and but for every n you need to look up a previous one. So now you kind of see why you want this initial rest condition, because you need a start point, and the starting point is your n0. So you start at n0, then you calculate y of n0 with those things, and with n0 those are probably all 0 because of the previous time step. You have the initial rest of them being 0, and so you sum this thing, then you have n0 plus 1, then you keep doing it. And do we have time? Yeah, we should have the time to see an example of doing this. And but anyway, let's see a special case. So a very special case is big N equal to 0. So big N equal to 0, then things become very easy because then it doesn't depend on previous y. So you are just summing over a whole bunch of x. Okay. Yeah, and yeah, and this just describe an LTI system, and anyway, you can calculate its impulse response, and it will become this thing. Okay? And so, well, you can check it out. It's LTI, so you put yeah, so you put x equal to delta of n, then it's very easy to see this becomes this. So just having a whole bunch of Bn here. Excuse me. And you see this is causal because for n less than 0 is all 0. Okay. and they only have value between n through 0 to m. Okay? And also this is finite duration, so maybe draw a picture is easier, better. So this thing just, but it is not super important, so I should do this very fast. But anyway, so it has some value of those bn divided by 0, and maybe some of them are negative. So I'll draw a negative. So anyway, h of n look like this. So something and up to, so this is up to m here. Yeah. Okay. And this is causal because all the negative part is 0. Yeah. And its a finite duration is up to m, so it's called finite impulse response. And finally, we have 2 minutes to see a more interesting example. Okay. More interesting example of solving the recursive equation. Okay. So we have the difference equation like this. And so let's see, right hand side then is like a first order. So y of n, then we have this y of n minus 1. And right hand side we just have x of n. Then we express it in the recursive form. So keep the y of n here and put everything on the other side. Y of n equal to x of n plus 1 over 2 y of n minus 1. And okay. Then we try to solve this with some initial condition. So we solve this with initial rest, and we say our x is delta function times k. So this is an impulse at n equal to 0. Okay, and then we can do the thing we described before. So we solve this recursively, and the initial point obviously is at n equal to 0. So we start with y equal to 0. Okay. So let's still draw this a little bit. And so this is k here. Okay, so this is x of n. Okay. And yeah, so you solve y of n start at n equal to 0. So then you see the y of 0, you sum it should be k. And the y of 1 will have, you solve this recursion, then you should be x1 will be 0 because x only have value at 0. And you have plus this 1/2 of the previous step. Then so it will be 1/2 of this. Then you see the next step, obviously the same thing happen, x of 2, all those will keep 0. And you just keep having those 1/2 of previous step. And yeah, and you see a trend, so y of n should be 1/2 to the n. Okay. So yeah, so this is what happened, the recursive thing, and obviously the infinite impulse, and yeah, we're over time. So any question? Otherwise, yeah, I think we are having everything we want to say. And yeah, so I have homework. I should have this kind of problem in your homework, I believe, the solving recursion.